This conference will now be recorded.
All right.
Now I have to really watch what I say.
Yeah.
So captured for posterity. So hi, good morning or good evening, wherever you are. I'm David Krukmeyer from Ventana Microsystems. You may have heard of us, you may have not. We're developing RISC-V processors in a chiplet-based in chiplet technology. And so, of course, because of that, we're developing also a die-to-die interface based on BOW. So I've been involved with the link layer group now for several years. And so we've at Ventana have gone off and we've built, we're basically building a full stack die-to-die interface on top of BOW. We've been in discussions with Boppy and a number of other people about presenting the link layer aspect of this. So what I'm going to present today is sort of a portion of the overall link layer, what I call the generic link layer. So it's the stuff that's kind of abstracted away from, or that abstracts away all the protocol level stuff that's that would be considered kind of a higher level. So this link layer is really kind of, you can kind of think of it as the step just before you get down to the physical layer. So it's sort of, and actually, why don't I just go ahead and get going, and I'll tell you what the services it provides in a few slides. So overall agenda here, we'll talk about the goals, and this is primarily Ventana's goals, but it applies, I think, in general as well. As I mentioned, I'll talk about the link layer services that this segment of the stack provides. An overview of kind of the stack and what portions, the various kind of subcomponents there, flow of information and flow control methods, our error detection and correction mechanisms. I'll talk a little bit about training, and then there's a virtual wire mechanism and some optimizations as well. Well, probably won't get to the optimizations, but it's a short slide anyway, so hopefully we'll get through all this. So high level goals here, as processor builders, we have a number of constraints, and the high level goals here, we're trying to make this simple, low latency, high scalable bandwidth, and extensible. And all the sub bullets here, they cover into a little bit more detail here. So in the case of simplicity, we're really focused. The ODSA, I kind of view this as ODSA has two camps, that the people that come from the die disaggregation camp and the people who come from the package integration camp. They sort of meet at this chiplet level, or this chiplet middle ground. And so our focus was primarily coming from die disaggregation. And so you can't get any simpler than a wire. So we wanted to try to maintain that abstraction for the die-to-die interface. So you see the picture over here. This is kind of our model. You have a requester. I don't know if you can see my cursor. Maybe I'll just do a.
Yeah, we can see it.
I'll just do the laser pointer here. So you can. This is kind of our model here. Is that you presume that there's a requester such as a CPU, and a responder is a memory such as a memory controller, and there's an on-die interconnect that connects the two. And so the simplest model is just to say, well, this is just the abstraction of a wire. We're going to break the package here, or break the die here, and the requester is going to sit on one die, the responder is going to sit on the other die, and these guys don't have to change at all. They speak whatever on-die interconnect, AMBA, TileLink, whatever custom interconnect protocol you want. And we just insert the die-to-die interface between there, and the requester and the responder are none the wiser. So that's kind of a simple model there. We liked BOW as a physical layer. It's simple, it's cheap, it's robust. The other parts of this is because BOW versus SerDes, we can get rid of a lot of the complexities of data recovery, CRC, those kind of things. So that was the the primary thing. What's the cheapest way to kind of affect or get a die-to-die interface into the system? Like I said, we're processor guys. Low latency is important, so we wanted to try to architect something that could be implemented with very aggressive techniques to reduce latency in terms of the number of cycles. Again, this is one of those things where BOW comes into because it has good latency characteristics. And we wanted to eliminate CRC and the overhead of serializing through CRC, and replay less was less of an issue here, but taking the tax to calculate CRC on large packets was not really interesting to us. So we use ECC style forward error correction. The link layer also, like I said, bandwidth is important. So we wanted to be able to scale up and down bandwidth based on the number of active slices as well as the different data rates. And in addition, we wanted to be able to implement the link layer on different process technologies and methodologies on either side of the link. So we actually support different link layer frequencies in the link layer. For example, on the processor die, it may be a frequency that's higher than the frequency that's on, say, the hub, what we call the hub die. So so not only did we want to support different data rates, but we also wanted to support implementation methodologies and have different link layer clock frequencies to achieve those data rates and have those be compatible. So so this comprehends different different ways or different frequencies on both sides of the die-to-die interface. And then finally, we want it to be extensible. So it's kind of modular in the way that it was composed, so that we could add more features and additional flows over time. So let's okay, we have a change on me. Now my slides won't advance. Here we go. There we go. So the generic link layer services, at first and foremost, we're supporting different protocols over this in our implementation, and so to make this sort of abstract, each protocol is defined by a number of channels. We just generically call those flows, and so for each flow there's the link layer, the generic link layer, really is responsible for combining flows into a single bit stream. And this is kind of a mux demux type function. So you have a bunch of different flows. It gets merged into a single bit stream that gets sent over the physical layer. And on the receive side, the physical layer, it comes off the physical layer into the link layer and unpacks it into the individual flows. And so in order to avoid any kind of head of line blocking or protocol deadlocks, there's credit-based flow control that's implemented on each flow to support non-blocking transmission. And at the interface to the interface to the upper levels is really, from a generic point of view, it's just a simple valid ready handshake. So this is there's no complexity there. If you're familiar with Amber protocols, that's similar to AXI, but CHI, for example, has this credit-based link layer. And so from a generic perspective, we just kind of abstract that away, make it ready valid, and so the internals of this is very simple. So the other area of are the other services here, error detection and correction, of course. So the link layer is responsible for making sure that the delivery is reliable. And to do that, we have SecDet ECC with 2 code word sizes, and so you'll see why we do this in a bit. But basically, there's a 32-bit code word that corresponds roughly to a header. There's actually some payload bits in there, but more or less a 32-bit header code word and a 128-bit code word for the payload. So link training and bonding, yeah. So again, this is when you put together two or more slices, you have a number of things to consider in terms of the alignment of those slices as they get transmitted. The BOW spec doesn't talk anything about bonding, so that leaves it to that means that function has to be performed at a link layer. So there's the link layer does some inter slice skew alignment. The way BOW is also defined is that there's a parallel interface to the link layer, and there's a sort of serialization, deserialization that goes on. And so within each slice, there's a phase alignment that also has to be done, because as the TX side and the RX side come out of reset, the state machines, the serialization, deserialization state machines may be in different states. And so you have to get those kind of aligned before you can have good transmission. And finally, virtual wires is another service that's provided by the generic link layer. So we have a way to take transitions on level sensitive signals and package them up as wires and send over events from the transmit side to the receive side, and then effectively propagate the assertion and deassertion of those wires. So I'll pause here, see if I've put everyone to sleep yet, or if there are any questions.
Not sleeping, but no questions.
All right, thank you. So this diagram kind of shows the overview of the steps that happen at each layer. And I'll do my standard disclaimer here and apologize for some of the terminology. Because this was kind of, this was developed in anger, and so despite some of the terminology may be a little bit more confusing for people who come from there might be out of context for people that have come from a more traditional networking background. And so I apologize. It was one of these things where just needed a term to go on. So in some cases, there's probably a better term, and I think if this proceeds towards a spec, we can change the terminology. So I'm open to suggestions here, but for now I'll just use our terminology, and hopefully that won't be too confusing where there's any incorrect connotations. So the view here that we have is that it's a 3-layer kind of thing. There's a transaction layer at the top that's more or less interfaces to this is the SOC side of things. And in the context of the generic link layer, this is, as I said, this is a bunch of flows and a ready valid interface. If you were interfacing to actual on-chip interconnect protocols, there'd be another translation there between, say, CHI and this generic flow-based interface, or AXI, or whatever. So
David, this is where diport kicks in, right? Where that to the north of the TX and the north of the RX, as an example.
That could be, yes, that's an example. Exactly.
Sorry, thanks.
Yeah, excuse me. I was just clearing my throat. There's a transaction layer, and this is sort of per flow, as I said. So on the transmit side, there's packetization and the flow control mechanisms, and on the receive side, there's flow control and depacketization. And as you'll see, that calling it packetization and depacketization is very generous. It's not really that complex. But this is this makes a good slide for trying to explain this to customers. So then,
David?
yeah.
So what you're proposing is everything within this black dotted box.
Yes, thank you for pointing that. I was going to highlight that, and that's exactly correct. Is that the generic link layer really is encompassed by this, and so even though I have drawn, or illustrated here a transaction layer and a link layer, the link layer I'm talking about today is really sort of this whole box here. But these are these apply more to the kind of your standard networking model. But really there's stuff that kind of leads in between the two, between these two things. And even this and even this diagram's a little bit kind of too. I would say that when it comes to the implementation, I'm sure most people are aware that these things kind of blend together. And one of the things that is really tough to do is to classify this function is is exactly implemented in the link layer, or this function is actually is precisely implemented in the transaction layer. And one of the things we're really focusing on is making this as lightweight as possible. So these divisions are kind of arbitrary at best. Right. But it sort of gives you a kind of classification,
right.
if you will, a good
No,
mental model. But
that works well. And then right below it is basically the bow interface at this point, and that could be run at different frequencies based on what people choose to, depending on the clock rate and the data rate that they pick.
Yeah, and what I'm talking about today is basically, yeah. So this stack, these stacks are both rate matched in terms of bandwidth.
Mm-hmm.
But this stack, for example, could be running at 1/2 the speed of this stack.
Right. Yeah.
And so the way that the link layer packs up various packets makes that very simple. So there's no, and in fact, there's no need to know what data rate the other side of the link is transmitting or receiving at. I'm sorry, not you do need to know the data rate. I mean you don't need to know the link layer frequency of the side you're paired with. So it's so we do some swizzling there to make that work out.
Thank you.
So just so the right half and the left half are actually the link layer on two different devices, right, of the picture. Okay.
Yeah.
And the right half and the left half can run at two different frequencies, is the point you're making.
Correct. Yeah.
And then the other question I have, which I should have asked in an earlier meeting, but how many cycles are you looking at? And you're thinking one or two cycles to go from the top of the picture to the bottom, right?
Yeah, it's very low latency. Yeah, and in fact, I would say we go through this in 2 cycles. And actually, we go through more of this. I would say this is probably architect cycles, so 1.5 cycles.
Right. Yeah. So all that layering is more a way of thinking about it, not then each box is in one cycle.
Yeah, exactly. It's very flat. And like I was mentioning before, each of these boxes really just corresponds to a way to sort of classify what's going on. But it also implies a level of serialization that doesn't actually occur in the design, because a lot of this happens in parallel. And one of the reasons we organize things the way we did is so that you could do a lot of things in parallel. And so in our use case, latency is king. We're less concerned of there are low power and energy conscious designs. Ours is not so much. So the development of this it was done to allow very very low latency implementation, which often means doing a lot of things kind of in parallel, especially looking at this kind of thing. An implementation wouldn't need to be done that. That's just a technique.
So the latency that you and Bapi were talking about, that the 1.5 cycles, that's just through the TX, or is that a sum of TX plus RX for just your?
Oh yeah, good question. Yeah, each side.
Okay, so that's 1.5 cycles, and then it's basically the delay, the latency through the transmit side of the bow interface. Whatever, how many nanoseconds, the TX plus RX of the bow interface, and then another 1.5 cycles to go through.
Correct, and again, it depends on it depends on your it depends on your implementation frequency, of course. And so we're running at a very high frequency, but in an advanced process. So even so, there's I would say, based on our experience so far, we're not seeing any timing problems even hitting that. So
what frequency are you hitting?
I would I'll hide behind behind the proprietary information for that.
Okay.
but you know, we had this in mind, you know, north of 1 gigahertz. So I think a lot of link layers are especially where we are now today in terms of process technology. A lot of link layers kind of assume about 1 gigahertz frequency and implementation, and so we're more aggressive than that. I'll say that much.
I remember Bappy asked for the OMI link layer, and that was considered, but it was said it was. I mean, that's obviously tremendously low latency, and a lot of similarity here. I guess that was considered and rejected. I think it was because it was too much for transceiver versus the bunch of wires, but it looks like you're doing the same thing. So why not use the OMI, and what's the difference between this and the OMI?
I mean, I can't definitively say because I'm not familiar with OMI, but I would say that it does not surprise me, because at the end of the day, there's only so many ways to do these things. So
right.
So could we be accused of reinventing the wheel? Possibly. So
the OMI is, you know, is there. It was worth to Bappy. You remember I think we took it in.
Yeah. So
the group had a bunch of questions that I think I gave a list of answers, but then it went dead. The communication went dead. So I guess it never got followed up.
Well, so we did discuss it in a couple of meetings. I think there was some sense that it was wedded to, or maybe wedded is the wrong word. There was a container structure which is a part of it, and I think that was the general. I'm going by memory here. The general concern was that the container structure maybe was not suited for this application.
Yeah, well, what it was bunch of wires was basically a parallel interface, and
right.
Obviously the transceivers were a serial interface. But in reality, my point was, well, maybe that makes sense for the low speed and the mid speed bow, but a high speed bow is 16 gigabits per second, which is really close to the 32 gigabits per second of OMI, and OMI runs it at 2 gigahertz. And in 7 nanometers. The earlier version was a 25 gig, and that was 1.6 gigahertz internal bus. It's open source.
No, it wasn't that side, Alan. It was the other side, and maybe we can go back and look at it at our Thursday meeting. But we did discuss this, and because it is the place where the Thursday meetings where we spent a lot of cycles on was not the southbound interface, but the northbound interface in this picture, and the container structure there. And I think hopefully if you wait a couple of slides, you'll find that David's proposal is a lighter interface. I hope it's in here. Is a lighter container structure. I think that's where we really spent some cycles.
Okay. Okay, well, yeah, it's just the answer I got in the email, Fred, was this is a parallel interface that you're doing lots of things for serialization, but this looks like this acknowledges that there's serialization going on.
And it's right, but it's in our heads, it's a different kind of serialization. Maybe we'll save that discussion towards the end of the talk rather than here, if you can hold that thought.
Yeah, I'm gonna have to run, unfortunately, but yeah, no, it's just a point that obviously it's there, it's proven, it's running, and
yeah, and we made a good
open source as well. Obviously, the RTL is open source at both the processor and the buffer end. So
yeah, and so we actually, I mean, that was something that was I was really keen on, given that it was defined and working. So, but maybe what we'll do is we'll have you come in on a Thursday meeting and we'll revisit it, but we can sort of redo the discussion.
Okay.
All right.
Yeah. Right. No, that's fine. I don't want to derail anything. I mean, if this is the way everybody wants to go, that's fine. It is, I guess, reinventing the wheel. But if it sounds like the adder of the entire link read and write of OMI is 4 nanoseconds. From the first command bit going into the TL in the first 72 bits coming back. So so basically we're in the same ballpark is what these guys are saying here. They're saying 1.5 clock cycles. So 2 clock cycles is a nanosecond.
Hold that thought, Alan. Well, what I suggest is we can always come back and revisit it and look at OMI versus this on a detailed comparison if we want to.
Yeah.
I don't think there was any desire. So hold that thought on this, because just look at the container structure, which is what the with the other and the northbound.
Yeah. These are details I didn't know. So I'm not saying this isn't the best way. I'm just I wanted to understand.
Okay.
Okay. Cheers.
Yeah. No worries. Thanks. Yeah. We can certainly do a comparison on a Thursday meeting. Sure. Let's see. Yeah. So a couple more things to just mention here, and go through these functions a little bit more detail and in the following slides. There's several different packet types we'll see in the next slide that on information flow is that we classify the things into different packets. There's a TLP or transaction layer packet, and then LLPs, which are link layer packets, and then those basically get mapped onto the parallel interface of the BOW, which as we mentioned before, gets serialized to, and it's really kind of a multiplier divider type thing. It's not serialization in a SerDes sense. But that's more like TDM type thing. And so the link layer supports 1, 2, or 4 BOW slices in each direction. So this diagram would show the information from the TX to the RX. If you're connecting 2 chiplets, there would also be an opposite direction TX to RX. And we support up to 4 slices in each direction there. And oh yeah, well, okay. So information flow.
Hey, David.
Yeah.
So a bit of an unfair question on the previous slide.
Sure.
But do you?
There are no unfair questions.
No, I mean, it's a sort of really abstract question I am hesitant asking, but anyway, do you have a sense of how, like, you guys were sort of looking after die disaggregation, right, in some sense, and what is the link between the requirements of that and how your link layer came about? Like, what did you toss out? What did you keep in? Because you said, okay, these are the needs of that type of design.
Yeah, I would say about half of it had to do with the physical layer, and then, well, so directly I would say about half of it had to do with the physical layer, and then indirectly the implication on the link layer because of the physical layer, right? And so taking sort of both physical short reach type environment versus maybe a more traditional PCIe environment where the whole stack and the PHYs and everything associated with that is really intended or has been designed to go across packages, over boards, through connectors, those kind of things. Whereas BOW is just a point-to-point thing on a substrate, and so when you start, it really kind of bubbles up from the selection of the physical layer, and so because of that, things like the error model and the way that things are transmitted and all that other stuff, that has implications both on obviously on the PHY layer, or the physical layer and on the PHY design, but it also kind of bubbles up into the link layer because now you make different decisions about error correction and detection and reliable delivery, and the error models are different and the error rates are different, and so we initially chose BOW because of or BOW because of its simplicity, and then building on top of that, it makes it a lot easier to design a link layer without as much overhead, because it's a much more limited use case. And from a die disaggregation point of perspective, right? Again, you're coming from the perspective of previously I just had wires, and I want to add as little on top of that as possible. So an on-chip bus is very simple, and we wanted to kind of preserve that abstraction as much as possible here. Versus, like I said, the package integration, you're likely starting from the perspective of, oh, I have a discrete, so I have a discrete, two discrete chips in different package parts. One might be on a card, one might be on a board, it might be going through a connector, So it's a very different starting point, I think.
Okay. All right. Thank you.
That wasn't unfair. That was.
Yeah, that was a good description. Thanks. So I guess because the sort of errors you're expecting are going to be extremely low, you're expecting that the error correction circuit is going to be pretty much 100%, and therefore you've got good data inside the die beyond it. Yeah. So on OMI, to be fair, that's a very good point. On OMI, there's retry mechanisms that you would have to put into the main processor if you did get an error over the link through the various interconnects. So so you don't need retry mechanisms here, is what you're saying?
Yeah, and a UCI. So just to since there's the hot topic, the UCIe, right? And that's looking at UCIe, they have a at least for carrying PCIe and CXL, they have a CRC and retry mechanism defined in the spec, right? And so it's still a little unclear whether that's required if you use the streaming link layer interface there, but yeah, you just make different design decisions depending where you start from.
That's a very good point. So I take that on board in terms of difference from OMI. So thanks.
Sure. Okay. So information flow. As I mentioned, there's packets everywhere. So really starting at that, I'm going to really talk more to the diagram here than to the bullets. So hopefully I won't forget everything in the bullets. But so this is divided into sort of a per flow process, and then so you can think of this as more or less the transaction layer process. And you'll see this is kind of where the functions blend in between the link layer and the transaction layer. But this dotted box really corresponds to processing per a packet per flow, and then eventually you pack things into link layer packets and assign them to fragments, which correspond to that correspond to each parallel interface on a BOW slice. And so diving down a little bit more detail, we start at the top with a protocol layer packet, and this is if you from the generic link layer perspective, this is just a pile of bits. It doesn't how it became sort of this payload is sort of from a generic link layer perspective is kind of irrelevant. So this is just a pile of bits, defined by whatever flow that has an interface to sort of higher levels in this stack. And so, for example, this could be a CHI request packet. You can easily packetize AXI, just the cycle by cycle transfers here. And that's one of the key things I think I want to emphasize here is that because our model is more or less just a wire, or kind of like a pipelined bus, we don't do anything to really examine. We don't do anything. It's I don't want to say dumb. It's not sophisticated. Maybe I should say that. But effectively, you can think of this as just an extension of an on-chip pipeline on a bus. So in the case of AXI, you might have these data transfers or data, kind of data packets that are bursts of data, back-to-back cycles of data. And so we don't do anything special there. because we're really just trying to keep things lightweight, and it makes things nice and rate matched, and everyone's happy. So there's no accumulation of things at this level. Any kind of accumulation gets done at a higher level. So this is really, again, very simple, like a pipeline bus. So that protocol layer packet is really the payload for the TLP. So we don't do anything. I'll talk about some optimizations later if we have time, but for the most part, the generic link layer doesn't do anything. It just says, oh, I'm going to slap on a header, and that's my transaction layer packet. So the TLP header here basically identifies the flow. We'll see that the header actually reserves some space for some credits, and that's where some of the protocol stuff kind of, based on transaction structures. So CHI and AXI, for example, have certain transaction structures, and so we dedicate some space in the header for credit exchange for the individual flows based on transaction structure. I'll talk about that a little bit later. But the header's very small. It's 12 bits, and that just extends the TLP. So they have the header and the payload portion of the TLP. Then what we do is we add SecDed protection on top of that. The first 26 bits really get packed up into what's called a header code word. And then the remainder gets broken up into 128-bit code words. I just show one additional payload code word here, but I've got more details on the error protection mechanism later. So then once the ECC is added, then we break things up into granules, which is a quantized TLP here. And the granule size is 32 bits. So if there's, in the case where, after you've gone through all these additions and modification, or, additions of header and ECC, if there's anything left over, we just pad out to the end. But we pad out to 32-bit granules. We don't pad out to 128-bit code words. So there is some inefficiency added here by this quantization. But it's the same level of quantization you see in something like PCIe and some other link layer things. So just trying to think if there's anything else. It'll come up later, I think. So then once you have each of these flows, basically what the link layer is doing at that point is packing these quantized TLPs and just basically stringing out these granules from each of the TLPs and putting them into an LLP. And you can think of an LLP as just basically a framing, kind of like a framing type packet. It's a fixed length of 512 bits. We have one header granule and 15 payload granules. And so that header granule, excuse me one moment. That header granule basically has framing information in it, and basically tells you where the each of the TLPs starts. And so it's also separately protected with a 32-bit code word. And one of the reasons we did this, so it's kind of a strange, in a lot of the protocols, or sorry, a lot of link layer, you'll see that there's some flits that are packed, and then they add an additional flit header on top of that, or LLP header on top of that. And so you end up getting kind of these weird non-power of 2 number of bits. And so when we were looking at this, we said, well, there's if you look at the way these things get transmitted for different data widths and different number of slices and all those different parameters, what happens is that if you have a non-power of 2, or if you have kind of, so let's say 17 granules instead of 16 granules in your LLP, you have another problem in terms of trying to synchronize and figure out where your packet structure is, or how your packet structure is laid out. And so by just limiting it to 15 granules of payload and one header granule, we eliminated one dimension. So if you think of having a non-power of 2 number of granules here, your header, your LLP header shows up on the receive side. Both, there's a temporal component in, in terms of which cycle. If you can't receive the whole LLP in one cycle, there's a temporal component that says which cycle is the header coming in. But there's also the spatial component that you have to find. So by making this, across all the parallel interfaces, and so by doing this, we eliminate the spatial component, and so the LLP header always ends up coming in on the same, effectively the same 32 bits, and it's just a temporal component depending on what your link layer frequency is relative to your physical data rates. So it actually, and it doesn't cause too much loss of overhead. So loss in terms of overhead. So it's actually design simplification here to make the receive side stuff go faster. And so instead of spending, say a 16:1 mux and trying to figure out where the LLP header is, and then try to decode what's in the LLP header to know where the TLP is beginning, et cetera, et cetera. We just know kind of right off the bat, in this cycle, the LLP header is here. These bits tell me where to look for my TLPs. So that's if you talk about, I mean, this is an example of where we tried to make things simple and have aggressive implementation techniques. And then finally, as I mentioned, LLPs sort of get laid out into fragments. Fragments just really represent the quantity of data that we present to the BOW slices each cycle. Any questions on this before I move on? Okay.
Hey, you got about 15 minutes, right? FYI.
Yeah, I know, I saw. So flow control, I'm not going to talk about too much. I think we're not doing anything special here. Just again, we need to avoid head-of-line blocking for protocol deadlocks higher up, and so each flow is treated independently and has independent flow control. And so there's resources on the receive side that get where we exchange credits for. One kind of thing that's interesting is that we have two methods to communicate credits. There's as I mentioned before, there's space available in the TLP header, and so we just reserve a few bits in the TLP header so that under high utilization, we don't have to interrupt the flow of data to exchange credits. So in some sense, we reserve a small amount of link bandwidth for exchanging credits when link utilization is high, and so you basically at that level you can exchange credits based on the transaction structure. So for example, take CHI. CHI has a coherent read request has a request packet in one direction, and depending on the CHI interface or the width of the data interface, you may have 1, 2, or 4 packets coming back the other direction, and then there's a completion acknowledgement that heads in the same direction as the request. And so in a case where you have 256 data packets, 256-bit data packets, you have a known relationship between the ratio of each of those packets in each direction. And so by doing that, you can sort of allocate these header bits in that same proportion, and then you don't ever have to worry about exchanging these credit TLPs. So the credit TLPs, though, those are useful when link utilization is low. You can basically greedily package up the credits and send them over the link, and so there's less of a where there's a pause in the transmission, you can get the link, you can send more credits over, and then you have the ability to start up the link when utilization gets high again. So anyway, the algorithm is really straightforward, but that's more of an implementation algorithm. The signaling itself is kind of defined by the link layer, and it's just a matter of the implementation to determine how to allocate credits into the header of these TLPs. All right, I will. So this is where some of the more interesting stuff comes in. As I mentioned before, we implement sec.ecc, both 32 bits. You can kind of think of those as header code words that consist of 26 data bits and 6 check bits, and then 128 bits payload code words of 128 data bits and 8 check bits. And so, not inconveniently, or not so by design, small code words can fit into a single granule. And so what's interesting about that is that I guess I should say in general, there's a trade-off between transmission overhead. So that drives you to wanting longer payload, longer code words, right? So the ideal thing is you have the longest code word that you can tolerate given your error, your reliability constraints or requirements, and so you want to try that drives you in one direction. But then what happens is then that drives up, that adds cost in terms of serialization, because you have to receive all of the packet to look at or all of the code word before you can determine whether you have anything to correct, or and so there's this efficiency versus protection trade-off. And so what we did is we decided we would protect the headers with 32 bits and the payloads with longer code words, because one of the challenges here is unpacking on the link layer on the receive side. One of the challenges is unpacking the single bit stream into multiple flows. And so by putting the protection into the code word, or by putting the headers into their separate code word, and making that code word a single granule, what that means is that you're always guaranteed to get all the header information in a cycle. It doesn't split across multiple cycles of transmission, or really on multiple cycles of receive on the receive side. And so you always get the granule. And what's key about that also is that you can kind of decipher all of the framing information and correct any errors in line quickly. So what you can do is, again, this is aggressive implementation technique, is that you can just look at all the received granules, and before you even know whether they're a TLP header or an LLP header, we do know that it's an LLP header, but before you even know that it's a TLP header, you can speculatively correct all of the code words, so that once you get the framing information and decode the LLP header, that gives you the pointers to the TLP headers, and those will actually be corrected for you by the time you get that information. So again, if you're driven by latency and you care about these things, and you want to have aggressive implementation techniques, this does allow you to implement decoding and correction, decoding of the headers, detecting of any errors, and correction of any errors in the headers. You can do that relatively quickly and in parallel and in line, and it doesn't cost you anything in terms of latency because all of that's done in parallel. Sorry, just a pause to get some water. So then we didn't want to add 6 bits to every 26 bits of data, and of course, so we have longer code words to offset that for the data, and those can be done. That does add latency, but those can be done sort of once you unpack things. Those can be done after the correction of the payload. The payload can be done after the fact. It's really decoding where the things begin. That's sort of the challenge at first. So this allows, like I said, the framing information to be decoded in parallel rather than serialized. And
Hey, so as usual, I have a question on the previous slide for us, but we're almost out of time. So I'll save it for a ask later. So why you need flow control? Why can't you just depend on the higher layer to provide the flow control? The link layer can just, let be more wire-like and get every byte and push every byte out.
well, that's why I said this kind of bleeds a little bit into the quote unquote transaction layer. So in a sense, yeah, I mean the real reason is that somewhere you have to implement that. And if you say that one of the purposes of the generic link layer, if you say that one of the services it provides is the combination of basically combining and breaking apart different flows to support different protocols, then you just sort of bite it off at that point. I
see. Okay.
So yeah, again, it comes down to where you define the layers and what services they provide, and so I know that the link layer, the link layer group has talked very much about.
But you could get the same effect by the link layer saying, look, I will only accept messages of this size. It's up to you to slice it into that message of that size, right? You could get roughly the same F.
Yeah, I mean, I think so.
Like I say, is it that, or is it just the basically like, if you said I literally accept only one flow from one particular thing, then you could sort of skip it here. But if you did want to accept multiple flows, then
no, even if you accept multiple flows, as long as you accept only fixed size messages from a flow, you can pass the burden of flow control onto the layer above you. You don't need to bite it off.
Well, or I guess said differently, if I understood it correctly, you're sort of saying if you're fixing the available bandwidth to each flow, and then they all get whatever it is that you pre-allocated.
Oh, okay. No, I guess we're out of time. I'll take this for a Thursday meeting. Sorry.
Yeah, no problem.
That's fine. I do think that, again, at the end of the day, the divisions of where what gets done at each level is kind of arbitrary. So it does drive you in different directions depending where you draw that line. And if I go back to my statement about latency is king, I didn't want to be too too strict about where classifying this as a link layer service or a transaction layer service or whatever, because at the end of the day, I care about talking a CHI transaction on one chiplet to a CHI transaction on another chiplet, or CHI message at actually even lower level. All I care is how do I get that from one end to the other, and so that our implementation kind of blurs all those things together for that reason. And so this is just this generic, what I'm defining a generic link layer was a convenient internal place for us to kind of draw the line. so it's sort of defined that what I presented today is sort of defined a little bit based on what we thought was an easy place to draw the line from our implementation, and it has the services that I discussed. But yes, you can draw the line. You can draw the line differently, and that drives you in different directions in terms of your design.
Okay, we're down to 3 minutes, I think. So we're losing people.
I can finish up this slide very quickly just to talk about the error rate. And I did this all modeling in a high precision package in Excel, so 200 decimal points of precision. So right. And so the these things, very rare events, rapidly exceed the precision of double, of IEEE double precision floating point. So anyway, I assumed a bit error rate of 10 to the minus 15th. Our 5 vendors assure us that it's much lower than that, but 10 to the 15th is a nice margin for us, and it's consistent with a lot of what other link layers assume. So using a bit error rate of 10 to the minus 15th and a data rate of 2 terabits per second, which basically corresponds to 8 slices at 16 gigabits per second. If you look at all the bits that get transmitted in 1 billion hours, at that data rate with that bit error rate, you end up with a probability of an uncorrectable error of less than 0.001. So it's a very robust. It seems like it wouldn't be, but because we come from the a lot of us come from the perspective of, oh well, PCIe, it's there's these burst errors, and again, the error model is important here, and so the assumption here is that the error model is random independent errors. There's no burst errors. That's the one of the primary assumptions. And also, we're basing it primarily on what gets used at DDR. So DDR has it's actually has similar data rates, but it actually has a much harder or much noisier electrical environment than BOW. So we kind of the starting assumption here is that the error model is very similar to DDR because the signaling is very similar, but it's actually better because the electrical environment is more constrained. So this is a good pausing point. If there are any questions here, I can answer some questions, and otherwise, thanks for listening.
All right, perfect timing. Thank you.
Thank you, David.
Oh, thank you.
Sure. Thanks a lot.
Very nice.
That's everything we wanted. Thanks. Hey, have a good weekend, everyone. I don't think there's a business group meeting today, so I'm going to end the bridge.
No, Bapi.